All right, number 67, draw a mapping diagram that represents the relation and determine whether the relation is a function. So when we do a mapping diagram, we have our inputs, x, mapped to our outputs, y. So we can go ahead and list our x values here. Mapping diagrams typically will have the smallest to the largest input. So if we look at our inputs, we have a -2, a 0, a 2, and a 4. So that actually looks like that is in order. So we have -2, 0, 2, and 4. And then our outputs, which is the y, -6, -5, -6, and -4. So if we order those, the smallest one we have is a -6. Then we have a -5. We had a couple -6s. You only needed to write it one time. And then we have a -4. All right, so what we're going to do now is map these. So the -2 will get mapped to the -6. All right, the 0 maps to the -5. The 2 will map to the -6. And the 4 will map to the -4. So there's our mapping diagram. Is this a function? So two ways you can tell if it's a function. If you're just looking at the ordered pairs, um, you cannot have any repeating inputs or x values. So we have -2, 0, 2, and 4. Those are all different. So yes, this is a function. What we can look for on a mapping diagram is here's our inputs. Are we mapping a -2 to more than one output? So see how -2 only has one output, 0 only has one output, 2 only has one output, and 4 only has one output. It's okay that -2 and 2 have the same output, but they each have, they're not mapping to like a second output. So like if this -2 was mapping to -6 and also mapping to -5, that would not be a function. So is this a function? Yes, this is a function. All right, number 68. The function f of x equals 34x represents the number of jumping jacks you can do in x minutes. How many jumping jacks can you do in 10 minutes? So they are giving us the value to plug in for x. So let's just talk about function notation. If they want to know how many jumping jacks can you do in 10 minutes, you're going to find f of 10. And that just means plug a 10 in for your variable. So our function is 34 times x. So we'll do 34 times 10, which gets us to 340 jumping jacks. And we look at our options and we can see choice D has 340 jumping jacks. Number 69, how are the functions f of x equals 2x plus 1 and g of x equals 2x plus 6 related? So we can see that our function changed. The slope is the same, 2x and 2x, but our y-intercept went from a 1 to a positive 6. So if we look at our options are translating, right? But translating correct, not right as in to the right. So what we want to do is see if we're going from a 2x plus 1 to a 2x plus 6, how did that change? So anytime that you guys have a change of your output like that, that is going to be vertical. So if you can kind of picture our y-intercept is 1 and a y-intercept went up to 6, it went up 5 units. It didn't go down 5 units, it went up. It didn't go to the left or to the right. So in this case, g of x got translated 5 units up. And then what we're seeing is the resulting function. So if I were to write this out, with the where we would see how the function changed versus just the resulting function, we could say, let me just show you what that would look like. G of x is equal to our f of x function plus 5. We also could write it g of x equals, now our f of x function is 2x plus 1 and then a plus 5 on the end. So anytime that you are changing a function with addition or subtraction, in this case both with addition, you are going to translate or shift your graph left, right, up, or down. When the addition or subtraction is on the end of the entire function, like it is here, here's our function and we're adding 5. Here's the 2x plus 1 and we're adding 5 to result in this. That's a vertical shift. Plus 5 means you'll go up 5. Minus 5, we would have gone down 5. All right, number 70, which of the following statements is true about the graphs of f of x equals 3x plus 5 and g of x equals 3 times x plus 1 plus 5? So what I want to point out is, can we notice how the function changed? So it was a 3, here's your 3, x, well, it's no longer just an x, now it's an x plus 1. And then your plus 5 is still your plus 5. So here is the change right there, x plus 1. So our changes with addition, anytime you bring in addition, it's going to translate or shift your graph, either vertically or horizontally. What's different about this one is that addition is with the x. We are adding a 1 to the x or to the input. That means it will be a shift of your x's. And if you think about where the x's are on a graph, that's your x-axis, horizontal, right? Left or right. So this is a horizontal shift. And then anytime that we're shifting our x's, it's going to be our tricky x. If it says x plus 1, we are going to shift in the opposite direction because that x is tricky, to the left one. And shifting and translating are synonyms. Those mean the same thing. So in these options, we see translating, and we might say shifting as well. So we're looking for the one that says we shifted or translated 1 unit to the left, and that is option D. If we were shifting that to the right, then g of x would have looked like 3 times x minus 1 plus 5. So see the difference in an x plus 1, we shift to the left, and x minus 1, we would shift to the right because of that tricky x.